Okay, for this one, I'll be talking about how ear works. Like how we talk about it in class, there is loud, loud, and then there's a quiet sound. Loud is when it becomes very painful, and a quiet is when it's barely, you can barely hear it, it's pretty quiet. And then there's also halfway there. And for loudness, it will be 1 watt over meter square. And for the quiet, will be 10 to the 12 watts meters over meter square, and where the half part will kind of be like 10 to the 12 over 2, which is like a half. But our brain don't work like that, so then they trying to convert it into a logarithmic way. So we use very little resources on the higher or loud noises, and then we have more resource on the quiet sound. So then the logarithmic scale is perfect for this kind of thing. So we talk about crickets in class, so then we use cricket as an example. So if we hear like about 1,000 cricket, how much do we need more to hear it? And in class we decided that it's about 10%, so then we'll hear it, because if we have 1,000 cricket and we only add one more, there would not be much difference. But if we have at least 10% of it, you can see the difference. But if we have like about one cricket and you add one more cricket, that will make a difference because the number is smaller. So if there are more then it needs to be a larger change, and if they're lesser, then there needs to be a lesser change. And how we talk about this is how intensity is. So then if they give us an intensity of 10 to the negative 7 watts meter per square, to change it back into the cricket, you need to take 10 to the minus 7 plus 12, which will give you the Bell scale, and that will be 10 to the 5th. And then you take the exponent of it. We get tired of writing the 10 to whatever power, so we only take the exponent. So then we write just 5, and that would be the Bell scale. And then you take that 5 multiplied by 10, which will give you the decibel scale. And you can do that with any number and it will be the same. And you can even do it backward, like how this example show. So if they give you a 40 dB, you will convert it backwards. So then 40, you divide it by 10 will give you 4, and then just put that to the exponent, and to get to the other, you take 10 to the 4 minus 12, and you will get 10 to the negative watt meter per square. And the same thing as this one, give you 30 dB, and then you divide it by 10 to get 3, take the 3 to the exponent, and take 10 to the 3 minus 12, and you will get 10 to the negative 9 watts meter square. And here's another example. This is where the explosion happened, and when the explosion happened, it was spread around 1 meter, and this is where the larger part happened, and this part is the part where it's smaller, and then there will be a larger circle spread, which would be 2 meter, and that is only not one half of intensity. And a half of intensity, it's over the square. So then you would take the 1/4, so that 1/2 to the square, that would become the 1/4 intensity. And if you have another one which they will spread out, and the area of a sphere is 4 pi r to the square, which give you this part. And so to get the third part, you get 1, and then over, since it's the third sphere, 1 over 3 to the square, which will be 1/9, and which is closest to 1/10, which means you lost 1/10 of intensity, and that means a loss of the 10 decibel. Okay, this is a tube standing wave, and I'm going to talk about, I can explain open, and open close standing wave. And this is your example, so I use this one, the one that you draw it out. Open, and open close. For open is an antinode, a node, and antinode, and that's the smallest one you can get. From an antinode to a node, it's a fourth of wavelength, and a node to an antinode is a fourth of wavelength, which equal a half a wavelength. And to give one full wavelength, you need an antinode, node, antinode, node, antinode, and that will give you 2/2, which is one wavelength. And an antinode, node, antinode, node, antinode, node, antinode, node, which is 1/4, 2/4, 3/4, 5/4, 5/4, and 6/4, which is the same as 3/2. And this pattern just keep continue going on. And we come to this equation that is length equal the integer of a wavelength over 2, but we are looking for a wavelength, so then we take algebra to do that, and then we get this. But we are also looking for frequencies, and frequency formula is the speed over the wavelength. And for us right now, the wavelength is 2L over n, so then we take frequency equal the speed over 2L over an integer, and which gives us an integer of speed over 2L. And for open closes is pretty much the same thing. It's alternate n and n, a and n. And for this one, a to an n, that is 1/4 wavelength. And then there's 1/4, 2/4, 3/4. And for this is 1/4, 2/4, 3/4, 1/4, 2/4, 3/4, 4/4, and 5/4, like how it's written here. But for that, the integer will have to be an odd number. So it's gonna have to be 4L over any odd number, and the frequency here would be any odd integer number of speed over 4L. Like this example, if you look at the Planck spectrum, the black one is the flute, and the flute one will go even, so then all the peak will be even peak. And if we switch that to a clarinet, it's open close, so then that will have a odd peak on each of the thing. And the lowest frequency for the flute will be V over 2L, and the lowest frequency for the clarinet will be V over 4L. And this one will give us the even peak, and this one will give us the odd peak. And we can look at this. There's this two tube. They both are exactly the same length, except one is open and open-ended, and one is open and close-ended. With an open-ended, it's only travel one round, so it will go push and then a pull back. And for the one that is close-ended, it will travel twice longer, which make the sound lower pitch. So it will go a push, back with a push, and then a pull, back with a pull, something like that. So then it will travel twice longer than the one with open and open. And like for this example, we can draw a box with a string, and then we have to find the matching frequency for it. So then this box will have some matching frequency to this string. This is the velocity, that's the string. So then we have to find the length of the box to match the frequency of the string. And we can have an integer of a sound over the speed of a sound, or time speed of a sound over 2L, which equal the integer of a tube times the speed over 2L. And to find the length, we have to find the length. So to find the length, you cancel those out and do some algebra. When talking about tube, we were also looking at these molecules, how they are working. So this one is open, open. For open, open, it and with an and for open, open, you can see that the molecule at the end here can move more freely than the molecule here, and you can see that on here, that's a node, and that's a node there. They're not moving, and these are the antinode, those ones that are moving. So we're having an open and open and a standing wave. These molecules move twice farther than those ones that are here because they have the space to move freely, and those ones in the middle here, they don't have that much space to move, and they're just repeating and doing the thing they are supposed to do. And this one is open closed standing wave. As you can see, it's closed this side, so right here the molecules are not moving, but here it's open, so it's free to move right there. So then, as you can see, it's kind of similar to the last one, but then this part right here, it's not moving because it's closed, and this part it's open and it moves. And you can see it from here as well. There are some parts that are moving and some parts that are not moving.